Hey, good morning, everybody. This is Mr. Aynesworth. We're going to get into the reciprocal functions here in AP Pre-Calc in section 4. But before we do, we're going to review the tangent function and go over some concepts that will hopefully give you insight on like why the tangent function acts like it does, or we say behaves like it does. And it's because it's totally different than the sine and cosine functions. So let's do what we always do, and let's analyze the domain first so we can determine the vertical asymptotes and put some ideas together here. Okay, so first thing we do is we have to understand that tangent theta is defined to be sine theta divided by cosine theta. Okay, so we're going to start there. We're going to write it as a rational function. And as you guys know, all rational functions have restrictions. Okay, so the question is, what are the restrictions here? Because we're trying to find the domain, which gives us information on the vertical asymptotes. You know, where is this function undefined? And we're going to go back to grade school as we always do here. And we have to remember one basic fact, and is that you cannot divide by 0. Okay? And wherever it's undefined is wherever the denominator is 0. So we say we cannot divide by 0. You never could and you never will. Because of that, one basic fact exists here. So the cosine of theta, whatever it is, it cannot be equal to 0. That implies that whatever angle makes cosine theta equals to 0 has to be excluded from the domain, as we're going to all reals accept those values, and those values become the vertical asymptotes of the function. So what we need to think is like, when is cosine theta equal to 0 on the unit circle here, and we exclude it. So I'm going to say theta is not going to be equal to, well, what angles? Cosine of what angles give you 0? Well, if you take a look at the unit circle here and recall, look at the x-coordinates here. The x-coordinate at the top of the unit circle at 90 degrees, or pi halves, is 0, and at the bottom is 0. And we know, because of prior experience here, that the cosine of pi halves, or 90 degrees, is equal to 0, and at the bottom here, the cosine of 3 pi halves, or 270, is also equal to 0. We know that. And if you keep adding pi and you go from the top to the bottom, back to the top, and add multiples of pi, you get those angles, and every time you get one of those angles, the cosine of that angle equals 0. So theta cannot be equal to, pi halves, 3 pi halves. That's at the bottom. Back to the top, 5 pi halves, etc. Okay? And the simple way to write that is that theta cannot be equal to pi halves plus k pi, where k is some integer. Okay, and if you don't know what an integer is, well, it's 0, plus or minus 1, plus or minus 2, plus or minus 3, and so on. Okay, those are the integers that you know of. And the period of tangent, as you guys know, is pi. It's periodic. Okay, and that's why we add multiples of the period. So this k pi, this term right here, this is multiples of the period. That's what it represents. Okay. Now, so we know the domain now. Okay, so this information right here, this is the domain. Okay, all reals not equal to these angles. And you also have to understand the domain gives you the information on the vertical asymptotes. So I expect vertical asymptotes at all of these angles. Okay, even negative pi halves and negative 3 halves pi, and so on. Because you can go in the other direction too, right? Okay. So now to kind of get an idea of the parent function, let's always go back to basics here. This is what we did in the beginning of trig, right? Instead of just going straight to Desmos, we evaluate a little bit and then we back everything up with Desmos. Okay, and I'm going to connect the unit circle here with what we're doing, just so you can see what's going on. And remember tangent theta. Yes, it's defined to be sine theta. Okay, sine theta divided by cosine theta. Let's jump ahead here. But it's also defined to be y divided by x. Okay, so when you look at these coordinates on a unit circle, right here, you can take the y coordinate divided by the x coordinate on the unit circle here, because the x coordinate is the cosine of the angle, and the y coordinate is the sine of the angle on the unit circle, as you guys already know. All right, so there's two ways to evaluate these functions at these angles. So let's get some experience here. So the tangent, okay, of negative pi halves, well, that's down here. Negative pi halves, that's a clockwise rotation. That's coterminal with 3 pi halves. And the the y divided by x ratio is negative 1 divided by 0. Okay, negative 1 divided by 0. And of course, guess what? That's undefined. And we already knew that was going to happen because we analyzed the domain first. So we have our first vertical asymptote by evaluating the function, which backs up what I said earlier, which is kind of nice. Now the next point here, we take tangent of negative pi halves, pi fourths. That also is a clockwise rotation. And as you guys know, if you take a look here, negative pi fourths is a clockwise rotation. And guess what? That's coterminal with this angle, 7 pi fourths. All right, and if you take y divided by x right here, which is your tangent ratio, you get negative root 2 over 2 over root 2 over 2, you get negative 1, okay? That's one way you could do that. Or you can simply look at the triangle here, the 45, 45, 90, and take opposite divided by hypotenuse, because we're dealing with SOHCAHTOA here. SOHCAHTOA. And tangent is the opposite side divided by the adjacent side. And that's going to be 1 as well, but it's in quadrant 4, so it's negative. All right, so this right here is negative 1. Let's keep going. Tangent of 0. Okay, if you're at 0 radians or 0 degrees, okay, you have 0 divided by 1. Okay, y divided by x, and guess what? That's 0. So it goes through the origin. The tangent of pi fourths, well, just look at the triangle. 1 divided by 1 is 1. See, there's different ways to think about it. You can use the unit circle, or you can simply use your triangles. I use the triangles, but you could do either one. Now, these next two angles, we're going to need Desmos here, so we're going to sidetrack. We need Desmos right there. And this one here, we don't need Desmos here, but we need a decimal. I need decimals for these next three angles. So we're going to use Desmos for all of them. So I'm just going to write it down and then go to Desmos and then approximate them as decimals because we're going to plot. And you're going to see something, and then I'm going to ask you some critical thinking questions. All right, so let's go to Desmos real quick. All right, so notice that I already have the functions and the table loaded. Okay, I want you to pause the video right now, right? And you guys know how to enter a function in, also create a table here. So go ahead and do that. So first type in the function, tangent function, and then use the gear at the upper, the top of the screen up there. Click on it. Convert your function to a table and then simply type in your angles and you'll get all these values. Okay, and we need these values here. So pause and the video now, go ahead and do that. And then I also put in my vertical asymptotes in here too. I want you to do that as well. And that way we can have a little discussion, okay? Okay, so I'm assuming that you have done that. So let's go ahead and let's bring over the values right here. So at 5 pi 16ths, it's 1.496 or 1.497, 1.497, and then 1.7, that's 1.732, and then 5.027. So we got some values. There you go. All right. And notice in Desmos too that we have, they even plot the points as you get them. So it's so cool right here. Look at that. Let's see here. Okay, so let's do this. Let's screenshot this. And let's bring this into our lesson. Just need the graph right there. Okay, and when you do this on the iPad, just say copy and delete. And then you just bring it into your lesson real quick off to the side. Okay, so click on the text mode button and then press and hold on the side. And then we'll paste it right in there. So cool. I love this technology and using it for instruction. Look at that. There we go. There's your graph. How cool is that? Okay, so we know what it looks like, and now let's do a little plotting here. All right. And let me see. Oh, I forgot to do this right here. So the tangent of pi halves. So that's at the top of the unit circle. So if you go to the unit circle here, 1 divided by 0. Ooh, that's undefined. Okay. Look at that, 1 divided by 0. We found another asymptote right here and right here, okay? So we know how to do it analytically in the beginning. We know it's multiples of pi halves plus k pi, right? Pi halves, 3 pi halves, 5 pi halves, and so on, because it's periodic. It keeps on repeating. All right, but we will also know how to evaluate the function now. Ooh, check that out. I didn't do that earlier in my previous lessons. Okay, we just discovered the asymptotes by Desmos. Here, I'm actually evaluating the functions. Look at that. Okay, so we have our asymptotes here. If you want to draw some more, go ahead. Okay, so we have a vertical asymptote at negative pi halves, at pi halves, at 3 pi halves. And then we want to plot the critical points in here. And so you always want to plot at least 3 points. Here, okay, and a 0, 0, and then pi 4 comma 1, and then you sketch the curve. Okay, and then you could use the period, which the period is pi in this case. We already know that. Okay, and then you sketch the curve here. So let's do that. So the question is, though, why does it behave like this? Why does it go infinitely up? Why is the range the set of reals? Why does it keep on increasing as you get closer and closer to pi halves? Like when you take the angles here and you get closer to the asymptote, why does the function approach infinity? Why does that happen? Okay, so I want to take a moment and talk about that and answer a few critical questions. Before we do, I'm just going to draw one more period. I'm just going to shift each of these points that I graphed. There's 3 of them right here. Pi units to the right. Okay, pi units to the right, pi units to the right, and pi units to the right, pi radians. Okay, and then you can draw another period if you want, just so you can see this thing. Okay, it's this nice curve, smooth curve. And it goes infinitely up to infinity and infinitely down to negative infinity. That's why the range is a set of reals here. But why does this happen? Why does it not have a max or min like the cosine and sine function? Okay, why is this? Well, we're going to answer these questions here. It says, why does this tangent function have a range of the set of reals? Okay, the range of this function, all right, is the set of reals. It's all real numbers. It goes infinitely up and down. You can, okay, recall the definition of tangent in terms of x and y. Okay, so let's do this. So let's take a look at tangent here of theta. I'm going to rewrite it in terms of x and y. And that's y divided by x. And then we're going to go to the unit circle here, and we're going to see what this really represents. What does the tangent ratio, okay, this is y to x, all right, represent on the unit circle? And then also, what happens to the slope of the radius of the unit circle, theta, as we increase from 0 to 2 pi? Well, if you look at the tangent ratio, okay, so let's go to this little circle here. If p is at x comma y, we're going to draw the famous right triangle in through here. All right, we get x here, and we get y here. X units to the right, y units up. And then the radius here is r. So we got a radius there. And notice right here, the tangent theta in this little diagram here is defined to be opposite y divided by x, right? It's opposite divided by hypotenuse. So, okay, and the tangent ratio is opposite divided by, excuse me, I back up, I think I said the wrong thing. Opposite divided by adjacent, okay? TOA, opposite divided by adjacent. I don't know what I just said, but it's supposed to be opposite divided by adjacent. Okay, so it's y divided by x, but what does that represent for the radius? And if you go back to, let's say algebra 1 for a second, so think back. Okay, this is called the run, and this is called the rise. And when you take the rise and divide it by the run, you get the idea of the slope, okay, of, in this case, the radius. Okay, so the tangent function gives you the slope of the radius at any angle theta. Okay, so given any angle of theta, you can calculate the slope by using the tangent function. Okay, so y over x, the ratio here, is the slope of the radius at any, okay, angle theta. Okay, that's what it is. So the question is like, as theta increases from 0 degrees all the way to 90 at the top right here, so we're going to rotate and we're going to rotate counterclockwise here, what happens to the slope? Okay, so starting at 0 degrees is horizontal, so the slope's 0, right? And then you got to visualize this because I don't have a little animation here, but if P rotates in a counterclockwise direction here, and it goes, and theta increases from 0 to 90 degrees, what's happening to the slope? Because it starts off at 0, slope's 0 here because it's horizontal, okay, at 0. But what happens as P rotates counterclockwise and approaches 90 degrees? And hopefully it's obvious here that the slope keeps getting steeper and steeper and steeper, okay, and it increases to infinity. And that is the answer to this question here. It says, what happens to the tangent ratio, or what does the tangent ratio represent? That's question number 1, actually. And this is question number 2. Well, so let's answer the question. So this it represents the slope of the radius, okay? So here we go. So the tangent ratio represents, all right, the slope of the radius, okay? Answer number 1, okay? Answer number 2, what happens to the slope of the radius of the unit circle as theta, your angle, all right, increases from 0 to pi halves, and that means we rotate, okay, counterclockwise, CCW, as I was saying in the diagram in the upper right, and the slope increases, all right, it gets more and more vertical, all right? The slope increases and increases to infinity until it becomes a vertical line. All right, so the slope increases to infinity and beyond, okay? It approaches a vertical line. Approaches a vertical line, which has infinite slope. Okay, so there you go. So if you didn't know the tangent ratio represents a slope at any angle, well, guess what? Now you do. Okay? And that's pretty cool. It can be used in many different situations, even in physics. Okay? And that's it for part 1. Okay, I wanted to analyze the tangent function here with you, starting with the domain, which gives us our vertical asymptotes. And then we evaluated the function by hand this time, backed everything up with Desmos, and then learned that the tangent ratio actually represents a slope at any angle theta, okay? And this is the end of part 1 in the series right here, part 1. In my next video, I will take a look at the cotangent function, all right, which is the reciprocal of tangent, all right? This is Mr. Aynesworth. I'll see you in my next one. Bye-bye.